Welcome to the deep dive. You brought us some fascinating, pretty advanced mathematical sources today. And we're diving in to see how they might just redefine what we thought was possible in algebra. Our topic: cracking the symbolic code of really big high degree polynomials. Our mission today, it centers around something that honestly looks like a monster on paper. We're talking a full 18th degree equation. I mean, just look at this. PSX by 18 by 17 plus 153 by 16 keeps going all the way down to a constant term plus 661 equals zero. That sheer length, that complexity, it's staggering.
It really is. And it's the perfect kind of challenge because, well, traditionally, an equation like this, its scale basically forces you towards a dead end, mathematically speaking.
A dead end. What does that look like? What happens in practice?
It looks like giving up on the exact answer. When you're facing 18 degrees of complexity, the classical methods, the ones you typically use, things like Newton's method,
Right. The numerical ones.
exactly, they abandon the search for a precise analytic solution. They just pivot entirely to iterative estimation, guessing, essentially.
So they don't find the actual root, they just find the closest possible guess.
That's it. You might get a number that's accurate to, say, 20 decimal places.
Yeah.
Seems amazing, right? But it's still just an approximation. And crucially, every single step in those iterative methods introduces a tiny bit of error, numerical error, rounding error.
Okay.
And with something as complex as an 18th degree polynomial, those tiny errors compound, they build up. So the final answer, while it might look close, could be fundamentally, well, wrong. You haven't solved it, not really. You've just sort of mapped the territory around the solution.
That difference between approximation and the actual analytic truth, that feels like the core of why we're doing this deep dive. We've sort of accepted these approximations for centuries, but these sources, they introduce something different.
Yes, exactly. We're looking at Ezouidi's theorem, and it presents a completely different way to think about solving these equations. It's designed to find the exact structural root. It's aiming to bypass the very limitations that have held back algebra for so long.
Okay, let's dig into those limitations first, because understanding the barrier, that makes the breakthrough feel much more significant, doesn't it? For the longest time, math has basically accepted that solvability itself has fundamental limits.
That's right. And usually, when people discuss the limits of solving polynomials, the big name that comes up is Abel's theorem, or more specifically, the Abel-Ruffini theorem.
Can you remind us, what's the gist of that?
Well, Abel's theorem essentially states that there's no general algebraic solution, meaning solutions expressed using radicals, like square roots, cube roots, and so on, for polynomial equations of degree 5 or higher.
Using just the coefficients, right?
Using just basic arithmetic and nth roots of the original coefficients, it basically drew a line telling mathematicians, look, for these really high degree equations, don't expect a neat, tidy, symbolic formula.
Okay, that's a major restriction.
Yeah.
So this 18th degree monster is way beyond degree 5. How does Ezouidi's method fit in? Is it saying Abel was wrong?
No, no, it's subtler than that. The Zouidi's method is important because it sort of excludes itself from, stands apart from classical methods that were, operating under the shadow of Abel's findings. It demonstrates that even if a polynomial might have roots expressible in radicals, or maybe its roots are complex structures that traditional algebra just can't neatly package, a different kind of methodology might still be able to extract the exact structural root anyway.
Interesting. So the limitation wasn't necessarily inherent in the equation itself, but maybe in the tools we were using.
Precisely. We're shifting from approximation, which is always going to have some level of error, to aiming for precise, solvable structural roots. It's just the sophistication of your solving method that dictates the outcome, maybe more than just the raw complexity of the polynomial itself.
So it's about finding the pure mathematical form, avoiding decimals until the very end.
Exactly. Keeping it purely symbolic for as long as possible.
But hang on, doesn't this just trade one kind of complexity for another? You avoid numerical errors, okay, but surely the computational effort of running a purely symbolic calculation recursively across 18 degrees, that must be immense, right?
That's a very fair point. The computational complexity is high, no doubt about it. But it's a different kind of complexity. Think about it like this. Numerical methods, sort of, pollute the calculation early on with those tiny approximations.
Okay.
With the recursive symbolic approach, you maintain purity throughout the process. It's like being a really intricate mechanical watch. If you use a gear that's just slightly off spec, that's your numerical approximation, the whole mechanism might eventually fail or give the wrong time.
Mm-hmm.
Symbolic recursion ensures every single piece is defined perfectly, symbolically, before you even try to put them together.
I like that. A structurally perfect symbolic clock. So, how does Ezouidi's theorem actually build this clock? What's the mechanism for maintaining that purity you mentioned?
Right, so the core idea is this recursive process. It systematically breaks the polynomial down and calculates these intermediate symbolic components needed to eventually construct the root itself. But, and this is important, we're not recalculating the original 18 coefficients of the polynomial px.
Yeah.
We're calculating a new set of coefficients, these special symbolic building blocks. We denote them as text words.
Okay, so these coefficients, they're like specialized parts for the final root, and you define them one by one using the previous one.
Exactly. They're determined recursively. The calculation for a ones component relies entirely on the pure symbolic results of the components calculated just before it. It's a nested step-by-step construction.
And what's inside that recursive formula? What are the elements that guarantee this symbolic purity?
Well, the formula itself gets pretty involved, but it fundamentally relies on three key symbolic pieces. First, you've got binomial coefficients, usually written as C. These are just combinatorial tools handling the counting and structure within the polynomial expansion. Pure math, no numbers needed there. Second, there's an adjustment factor, something like x or k. This is based on a chosen starting point or base coefficient. Again, handled symbolically. And third, the formula explicitly references earlier terms in the polynomial itself and crucially previously calculated Norse's terms, like sever a k. The absolute key is that all these parts, the binomials, the adjustments, the references to previous steps, they are all manipulated purely symbolically at every single stage.
Right.
We're just moving symbols and structural relationships around, not plugging in decimal approximations anywhere. That's how it sidesteps the whole problem of numerical error and aims for that pure structural truth.
That sounds intense, very structured symbolic buildup. So now let's apply this engine, this recursive calculation, to that massive 18th degree polynomial we started with. What actually happens when you calculate these text coefficients?
This is where it gets really interesting, maybe even surprising. This is where the hidden structure inside that seemingly chaotic 18th degree polynomial starts to reveal itself. Logically, you'd expect this recursive process to turn out, 18 incredibly complicated, non-zero symbolic components, right? One for each degree, essentially.
Yeah, that seems like the most likely outcome. Given 18 terms in the original equation, you'd expect 18 complicated results.
But that's not what happens. Instead, we find this amazing pattern of simplification. The calculated symbolic components, these text-to-theory values, they almost entirely vanish. They calculate down to zero.
Wait, almost all of them. So you go through this whole complex symbolic calculation, and the result for most of the components is just zero.
Precisely. It's quite remarkable if we look at the specific breakdown for this 18th degree polynomial.
Yeah.
The symbolic components for Cutco, $01 all the way to $0, that's 730. Every single one of them calculates out to be exactly math Kyoto. And then it happens again later. For K $10 up through K $16 dollar that covers through 60, they also all calculate to math B.
That's incredible. We're talking about potentially dozens of intermediate calculations, right? With complex formulas involving the original coefficients, binomials, powers,
Yes.
and they just structurally cancel out.
Yes. The underlying math shows how the specific structure of the original polynomial's coefficients interacts perfectly with the recursive formula for those specific k values, like k all 1, k4, k4, k or 7, 7, so that everything nets out to zero. It tells us this wasn't just a random string of 18 coefficients, it was a highly structured polynomial hiding a simpler form.
Okay, so if, let's see, 8 components zero out at the start, and then another 7 zero out later, that's 15 components gone.
Yeah.
Out of 18, that leaves only 3 potential non-zero ones. Or wait, the indices are a bit tricky. He survived.
Good catch on the indices. It means that out of the possible symbolic components influencing the structure, almost all are zero. The only ones that don't vanish, the ones that carry the essential structure of the entire equation, are sim 17 and 17. Just
Only two. And what do they look like? Are they still horribly complex?
They are specific and defined purely symbolically, but they capture the essence, we find. Says calculates symbolically to be 480,619 times 180,91, a large number, sure, but defined precisely. And the 17 calculates out as $480,618 plus 661 times 1818. Again, defined purely in terms of integers and powers.
Okay, so you have these two non-zero symbolically defined components. What happens when you plug those back into the general structure that Ezouidi's theorem uses?
That's the real payoff. The original polynomial, Ps from x, which started as this sprawling 18-term expression, collapses dramatically. Because all those other terms are zero, it simplifies too. Pi x by 18 by 9 plus s17 is nullars.
Hold on, look at that. 6 by 18, then a $17 term, then a constant term. That doesn't really feel like an 18th degree equation anymore, does it?
Structurally, no. It's essentially become a quadratic equation. Just think about it. If you make a simple substitution, let light by $9 then.
Then 6 by 18 is 22.
Exactly. The equation becomes just $20y plus s17 a dollar.
It's a quadratic in disguise. Hiding inside that 18th degree monster was a simple quadratic structure related to 6-9 derived.
That's the secret the symbolic version uncovered. Something numerical methods, with their approximations, would likely never stumble upon. They'd just give you 18 approximations.
That is genuinely powerful.
Yeah.
Like unwrapping a huge, complex package to find a small, perfectly simple mechanism inside. Okay, so now we have this straightforward quadratic form for Yetis, which is $699. We can solve that using the standard quadratic formula, right?
Absolutely. We solve for Yallers, which gives us the value of $6.09. We just plug our two non-zero symbolic coefficients and 17 into the familiar quadratic formula.
And then presumably take the 9th root to find x. What does that final symbolic root look like? Is it clean?
Well, clean might be relative here. Because we're solving for 6 skulls from 6 number, the final expression has to account for the 9th root, which introduces its own complexity. The exact symbolic structure for 6 looks like this. 6 doubles 1 plus left, 4c right, 4 right, frac to $1. Let me substitute those values back in. Right, it becomes $6 1 plus left, 4 619 times 161 times 18 right, frac 1 plus left. Or simplify slightly inside the square root. $6 none plus left, frac 4 619 times 1 plus left times 18. Right, frac 4 $6 times 18 plus leftovers. Or $6 4 46 frac 1. Work is approximately using the number provided earlier inside the square root. $6 right, frac 1 plus left, or 4
Wow, okay, that expression is intense. You've got huge numbers, the $18 term, that plus or minus from the quadratic formula, the square root, a fractional power, and even complex numbers involving Belleute and the complex part, the $2 use.
Oh, that's the mathematically precise way of capturing all the roots. Remember, we solved for y by $999. Any non-zero number actually has 9 distinct 9th roots spread out in the complex plane.
Right, roots of unity.
Exactly. That fractional power, the $19 nullars, combined with that complex exponential term involving $2 nullars, it's a compact way to represent all 9 possible distinct analytic solutions for $6. This isn't just an answer, it's the complete structural definition for all the roots of that original 18th degree polynomial, purely symbolic.
So let's recap this journey. We started with this incredibly intimidating 18th degree polynomial. We recognized that standard numerical methods would only give approximations, riddled with potential errors. Then we deployed Ezouidi's theorem using its recursive process to calculate these pure structural eyes components. And that process yielded a huge surprise. Almost all those components calculated to zero, revealing a hidden simplicity. The monster polynomial collapsed into just a quadratic equation, but in terms of $6.
And because we kept everything symbolic, that simplification allowed us to derive the exact symbolic root structure, avoiding approximation entirely. It really shows that sometimes the difficulty isn't inherent in the problem, but in finding an analytic method sharp enough to see the underlying structure.
This feels like it really shifts the conversation around those perceived limits in algebra. If this kind of systematic recursive approach can reveal such deep simplicity in something that looked impossibly complex, what does that say about the boundaries we thought existed?
It certainly suggests that maybe some of the limits we perceive, the kinds of restrictions people often associated with theorems like Abel's, perhaps they reflect the limitations of our methods more than fundamental limitations of the polynomials themselves. Maybe some things aren't unsolvable, just unsolved by current techniques.
So here's the thought we want to leave you with, something to think about until our next deep dive. If this symbolic recursive approach showed that a seemingly intractable polynomial was just a quadratic in disguise, what other problems out there, maybe in physics or cryptography, even chemistry? Problems currently tagged as unsolvable or only approachable through simulation might just be waiting for the right symbolic perspective, the right recursive lens to reveal their own hidden, simpler structures.
Definitely something to ponder. We'll start preparing the next stack of sources for you.
We'll get you next time on the deep dive.
Today, we're going on a bit of a mathematical adventure. We're tackling a problem, a real monster of a problem, that was considered completely unsolvable for centuries. But a revolutionary new way of thinking has finally cracked it wide open. So, let's dive in. All right, take a look at this. This is our challenge. It's an 18th degree polynomial, and yeah, it's a beast. For the longest time, finding the exact answers for x in an equation like this wasn't just considered difficult, it was literally thought to be impossible. And you know, this isn't just some random homework problem. For centuries, equations like this one represented a huge brick wall in mathematics. There are famous theorems, like Abel's theorem, that basically suggested that you couldn't solve general equations of degree 5 or higher with a simple formula. They were, for all intents and purposes, unsolvable. So, if they were unsolvable, how did people deal with them? Well, they had to settle. They used numerical methods to find approximations. Now, these methods can get you pretty close to the answer, but they're not perfect. They introduce tiny rounding errors, and at the end of the day, they only give you a best guess, not the actual precise solution. And this is where it gets really interesting, right? It's all about the philosophy of the approach. Think of it like a detective story. Traditional methods are like a detective giving you a list of likely suspects. You're in the right neighborhood, but you don't know for sure. Ezouidi's theorem, that's the detective handing you the DNA evidence, the security footage, and the signed confession. It gives you the culprit's exact identity, the precise, error-free, actual answer. So, this brings us to the hero of our story, Ezouidi's theorem. Now listen, this is not just a slightly better mousetrap. The source material makes it clear this is a whole new way of thinking that bypasses those old limitations. It basically walks up to those old, unsolvable ideas and shows that actually, these complex problems can be solved exactly. Okay, whoa, don't let your eyes glaze over here. You don't need to understand every symbol on the screen. Just focus on the idea behind it. This is a recursive formula, which is really just a fancy way of saying each step builds perfectly on the one before it. It's like a set of dominoes, all lined up, ready to reveal the pattern. And that crazy looking formula really just boils down to a super clear 3-step plan. First, we restate the equation using a new set of symbols. Second, we use that step-by-step formula to calculate them. And finally, we use those results to find the exact answers. Simple as that. All right, you ready? Let's put on our detective hats. We're officially starting the investigation, calculating these symbolic coefficients, our clues, one by one to solve the mystery of this equation. Okay, our first clue comes back, and it's a 0. Huh. Let's check the next one. S1R, also 0. And the third one, S2R, is 0 again. At this point, you're probably wondering, is this thing even working? And the pattern just keeps going. The next 5 coefficients in a row, all 0. It might feel like we're hitting a total dead end here, but trust me, these zeros are actually the most important clues we could have found. And then, bam, this happens. The 8th coefficient, S8R, is not 0. It's this absolutely massive number. And this right here is the breakthrough moment. This is the smoking gun, the crucial piece of the puzzle that changes everything. After that bombshell, we run the rest of the calculations, and what do you know? They're all back to 0. This just confirms it. That
One huge number we found was the unique critical clue we were hunting for. So, what have we got? A long string of zeros and one very, very important number. The investigation is over. It's time to put all the clues together and reveal the answer.
Let's ask that critical question. Were all those zeros just a waste of time? Absolutely not. They are the key to the whole thing. What they're telling us is that most of the complicated, messy terms in that original monster equation are, well, they're irrelevant. They all cancel each other out in this beautiful, elegant way. Because of all those zeros, our mathematical monster just collapses. It simplifies dramatically into this. Look at how clean that is. Our intimidating 18th degree polynomial was really just a simple quadratic equation in disguise the whole time. And from that much simpler form, we can directly pull out the exact symbolic root. This right here is the solution. It's not a close enough guess. It is the precise answer. The culprit's true identity, uncovered by relentless logic. So the thing to remember is that this is so much bigger than just one clever trick for one hard problem. This represents a fundamental shift. It redraws the map of what we even consider possible in math. This quote from the source material just says it all. This redefines the line between what we can guess and what we can know for certain. I mean, think about fields like cryptography or orbital mechanics for space probes, where a tiny rounding error can lead to total disaster. This shift from close enough to exactly right could be a revolution. And that leaves us with a really fascinating thought. If a problem that stumped the greatest minds for centuries can suddenly be unlocked just by looking at it from a new angle, what other barriers are out there just waiting to fall? What other impossibilities in science, finance, or engineering are just one new idea away from revealing their own elegant solutions?